Alright, hi everybody. Basically, I'm going to try and make this fast. The only reason I'm showing you this slide right now, obviously, you're not going to have to do bell work. I'm not here, but those are the first questions for chapters 16. That's 16.1 and 16.2. I'm going to go through the PowerPoint as quickly as possible. I'll try to make it make sense. Obviously, you don't want to just sit here and listen to me for a whole bunch, but hopefully this will work out. Alright. So, chapter 16 is all on solutions. We've kind of done 15 and all of the vocab that goes along with that. I can still help you if you need to, but what we need to get through today are solubility curves because you're going to get a worksheet here in a minute, and there's going to be a lot of questions on there, so let's get started. First of all, solutions. You'll notice in this picture that the molecules themselves line up in a way so that the negatives on water, for example, which in this case, water is your solvent. The solute is sodium chloride, and the positive charges on the sodium are surrounded by the negative charges on the water. Opposite here for chloride. Chloride has a negative charge. The positive hydrogens surround it. Okay, so this is called the solvation process, all right? The general rule here is that like dissolves like. This PowerPoint is on Canvas, so if you want to look at it later, I just want to point out a couple of things. So, whether or not a solute will dissolve in a solvent is really determined by charge and polarity. Okay, so when this term here says like dissolves like, remember water is extremely polar. At hydrogen bonds, okay, ionic compounds are like turbopolar. They're so polar they don't share anymore, so the positive ions will float off and be surrounded by the negative ions in water. What you need to kind of know from this is that means that polar solutes tend to dissolve in polar solvents. Opposite is also true. Nonpolar solutes will dissolve nonpolar solutes will dissolve in nonpolar solvents. Just kind of keep that in mind. We'll talk about it more later. Okay, so how can we increase the rate of something dissolving? Pretty simple. You can stir it. That increases the rate. If you think about the kinetic energy, you're moving them around, so there you go. If you heat it, the particles are now moving faster, so they're able to dissolve more readily. The smaller they are, so I always use the example, what if I had a sugar cube versus the same amount gram-wise of powdered sugar? The powdered sugar is going to dissolve faster because it's more spread out, the water can get to it easier. Alright, this is what you need to know. Okay, this thing right here is called a solubility curve. What you really need to pay attention here is the units and the scales, okay, the sides. You'll notice the solubility here is in grams of solute dissolved per 100 grams of water. What these lines represent is what is called the saturation point of these different solids. So these tend to be solids right here. So potassium nitrate's a solid. Temperature is on this scale. Solubility per 100 grams of water is on that scale. Again, water is like 99% of the time the solvent we talk about. Okay? So this is how much will dissolve. So you can ask questions like, at 60 degrees, how much sodium chlorate will dissolve in 100 grams of water? Okay, so you could go to 60 degrees, you go up to the line that represents sodium chlorate, and there you go. You can say, oh, that's about 138-ish, all right? So these lines represent what is called when it's saturated. Now, some other terms, and I'll probably come back to this slide in a minute, but let's go forward. If you have less dissolved than can dissolve, it's unsaturated. And you can actually have situations, which I know this sounds weird, but more solid dissolved than should be dissolved. That's called supersaturated. And typically, this picture is trying to show you that. I'll have a demo when I come back. But you'll add a crystal, and then all of a sudden, all these crystals will come out of solution. So it's almost like it's just stuck there for a minute. Okay, and then when you disturb the solution, a whole bunch of it will come out. All right. Other words, if they can be mixed in any ratio, they are miscible. So alcohol and water is a good example of that. It doesn't matter how much alcohol or water you stick together, they always mix. And if they don't mix at all, like this is oil and water, that is immiscible. So if they never mix at all, they're immiscible. All right, so let's go look at another solubility curve. Again, really important that you notice this is per 100 grams of water. So let's say I said, here's my sodium nitrate curve at 30 degrees, about 96 grams of sodium nitrate will dissolve in 100 grams of water. But what if I said, how much will dissolve in 200 grams of water? Well, it's 96 times 2. So they have to specify how much water, all right? What will affect this? Well, obviously temperature. So if you look at your solubility curve, temperature is a factor. You'll notice that solids, most of these are solids, right? But HCl, NH3, SO2, what those all have in common, their slope is going down. Those are all gases. And this has real world applications. So for example, in the summer it gets really hot. Fish do not breathe water. They breathe dissolved oxygen in water, which is why if you have a fish tank at home, you might have an aeration stone that just blows bubbles through the water. That's dissolving more oxygen in the water. The hotter it gets, the less oxygen can dissolve. So in small ponds, if it gets really, really hot, you can actually have fish suffocate. They suffocate, drown. They don't drown, but that's because they run out of dissolved oxygen. So the higher the temperature gets, the less gas tends to dissolve in the water. Polar ice caps have huge amounts of biomass. Okay, so the water underneath the polar regions, tons of small animals because there's a lot of oxygen. Pressure can also affect it. This only works for gases, all right? So if you increase pressure, more gas will dissolve. This works in like Pepsi, so that's why those are packaged under pressure, because it actually forces the CO2 to be dissolved more. And then as soon as you pop the top, it go, you hear the kss sound. That's all the gas coming out of solution, and then there's a bunch of bubbles. Okay, so these solubility curves really important. All right, let's say I had 90 grams of NH4Cl dissolved in 80 degrees of water. So 90 grams, 80 degrees, what's that called if I had this much? That's supersaturated, okay, and that can happen. If I had 40 grams dissolved at 80 degrees for NH4Cl, that's unsaturated. The line represents saturation, okay? So if you're not quite sure what I've been talking about, ask Mrs. Berger. She'll be here. Again, you're going to get some worksheets. You can always go back in this video and hit pause. The PowerPoint itself is on Canvas, so you can look there. But you're going to get some worksheets now on solubility curves. Help each other. Ask Mrs. Berger. Thanks, everybody, and I'll see you tomorrow.